Swayam Prabha. Digital India. Educated India.
Welcome to the lecture series on cello foundations again. I am going to continue with the estimation of settlement, that is the total settlement. We have discussed the procedures to determine immediate elastic settlement, the consolidation settlement and the settlement for granular soils based on various laboratory and field investigations. Now, today I am going to discuss the secondary consolidation settlement, and as we know that this secondary consolidation settlement takes place after the primary consolidation process is over. So, another component of total settlement is the secondary consolidation settlement. The secondary compression or creep continues much beyond primary consolidation and occurs at a slower rate, much slower rate than the primary consolidation. Though there is some doubt regarding the point of time at which secondary consolidation can be said to begin, it is quite clear that it occurs at a constant effective stress and is not associated with the dissipation of pore water pressure. One line of thinking is that the secondary compression is due to the gradual readjustment of the soil skeleton after the disturbance during primary consolidation. The rate of secondary compression perhaps is controlled by the highly viscous adsorbed layer surrounding the clay particles. There is now a general agreement that the magnitude of secondary compression can be expressed in terms of the secondary compression index C alpha given by the following equation, and C alpha is given as delta E upon delta log of T, where delta E is the decrease in the wide ratio in a plot of wide ratio versus logarithm of time corresponding to a time interval of delta T. So, this delta T is corresponding to time delta T, not corresponding to time delta sigma, as that is in the case of the primary consolidation. C alpha is measured as the slope of the straight line portion of the dial gauge reading versus logarithm of time curve, which is obtained by the primary consolidation. This curve we use to determine the coefficient of consolidation, and we find that after the primary consolidation is over, there is decrease in the volume of the specimen, and that is primarily due to the secondary compression. The compression is noted from the plot usually for 1 log cycle of time. So, whatever is the corresponding delta E, that is nothing but the value of C alpha. A typical plot is shown in the next figure. So, this is the figure. What we do in the consolidation test, we take the deformation dial gauge reading, and corresponding to those deformation dial gauge reading, we can get the value of wide ratio at any particular time during that particular stress range. Let us say we have conducted a test for a stress range of 25 kilonewton per meter square to 50 kilonewton per meter square. So, starting from 25 kilonewton per meter square, we can find out what is the wide ratio, and then at different time intervals we can find out the wide ratio, and then we plot as a curve between the wide ratio and the log of time t. Now, from here to here, this is the portion which corresponds to the primary consolidation, and this portion corresponds to the secondary consolidation. Now, theoretically this portion should be asymptotic to the time axis, but practically we see that this part of the curve is not asymptotic to the time axis, and hence using the theoretical curve we can find out the point corresponding to 100% degree of primary consolidation. So, what we do, we draw a tangent to these two straight lines, wherever it intersects we say that this point corresponds to 100% degree of consolidation, and whatever change in wide ratio is, that is due to the secondary compression. It means that above this is the part of primary consolidation, and below this is the part of secondary consolidation, and the line of this slope, the slope of this line will give you the value of C alpha, and normally it is measured for 1 log cycle. So, in this manner we can find out the coefficient of consolidation. Separating the primary and secondary compression is in a clear cut manner is rather tricky, especially if the soil is thick. In a thick layer, while parts of the layer which are very close to the drainage surfaces may have no excess pore water pressure, and in them may thus already be under secondary compression, whereas the parts which are away from that, it means that in the middle of the layer you will find that they are still a far way off from completing the primary consolidation. C alpha may decrease as the thickness of the layer increases. Another factor, namely the ratio of applied stress increment to the existing overburden pressure, that is delta sigma dash by sigma 0 bar, also said to influence the significance of secondary compression relative to the primary compression. Greater the ratio, smaller the significance of secondary compression. Also, the value of C alpha is itself not a constant, but may change somewhat with time. In spite of all these uncertainties, working values of C alpha can be determined by assuming that the influence of the factors mentioned above is negligible. As long as the stress increment is large enough to go well beyond the pre-consolidation stress sigma C dash, the ratio of C alpha upon Cc, that is the compression index, can be considered approximately constant over the normal range of engineering stresses. Masry and Godlewski 1977 gave values of C alpha upon Cc ratio for a variety of natural soils. According to these authors, C alpha by Cc has a median value of 0.05. The higher values of C alpha upon Cc up to about 0.11 were exhibited by peats and certain organic soils, while for inorganic soils the range is from 0.025 to 0.06. Lord in 1976 has suggested that for the normally consolidated soil, C alpha can be determined as C alpha in percentage equal to 4 to 6 times of Cc by 1 plus E0. The secondary consolidation settlement is worked out from the following equation, knowing H0 and EF. EF is the final wide ratio after the consolidation process is over for a particular stress increment. So, SS will be given by delta E upon 1 plus EF into H0. In the case of secondary consolidation, the value of delta E is not related to the stress increment, but it is a function of time and is equal to C alpha times delta log of t. So, in place of delta E we can write this as C alpha delta log of t, and the expression will be SS equal to C alpha delta log of t by 1 plus EF into H0. So, in this manner we can find out the consolidation settlement also. So, the total settlement will be equal to the initial or immediate settlement, then plus the primary consolidation settlement, and then the secondary consolidation settlement. Then we will discuss the allowable settlement. What should be the allowable settlement for different structures? Now, relationship between the total and differential settlement. We know that settlement is of two types, one is the total settlement, another is the differential settlement. We have already seen that the total settlement is not that important as the differential settlement. While it is relatively easy to estimate the total settlement, it is very difficult to estimate the differential settlement by means of a rotational analysis. For all practical purposes, it may be enough to use an empirical relationship between total settlement and differential settlement, which is normally less than the total settlement, and specify the design criterion merely in terms of permissible total settlement. This relationship is a function of the type of structure. Jerome in 1963, observations on actual buildings resting on granular and clayey soils are presented in figures shown next. Part A gives the relationship between the maximum angular distortion delta by L and maximum differential settlement. Part B shows the relationship between maximum differential settlement and maximum total settlement. Maximum distortion is determined by the differential settlement between adjacent columns, whereas the maximum differential settlement can well be between two columns which are far apart. So, these are the curves presented by Jerome for the case of sands. So, this is the maximum delta by L, and corresponding to this maximum delta by L, this is the maximum differential settlement. So, for that maximum delta by L, we can find out the differential settlement, and corresponding to this differential settlement, here from this maximum differential settlement we can find out the maximum settlement. Now, this is a straight line fit for the case of sands. Similarly, for the clays, this is the relationship between maximum delta by L and maximum differential settlement, and here in the case of clays, this is the relationship for the case of rigid footings, and this is the case for the case of flexible footings. A study of these figures indicate that in granular soils, the minimum differential settlement in some cases be close to the maximum total settlement, whereas in clays the differential settlement is much less than the total settlement. Maximum differential settlement generally does not exceed 75% of maximum total settlement in granular soils, whereas in clays it seldom exceeds 50% of the maximum total settlement. Now, these are the limiting values of the angular distortion that depends on the type of the structural problem. So, this table gives for different type of structures the value of the angular distortion which can be permitted in that particular structure. Like in the case when there are difficulties with machinery sensitive to settlement, this delta by L angular distortion is kept 1 upon 750. Similarly, for other cases also, for example, limit where tilting is of high rigid buildings may become noticeable, we will have to keep this angular distortion as 1 upon 250. So, the various values of the angular distortion which can be permitted can be seen from this particular table, and from this delta by L we can find out maximum differential settlement, and from the maximum differential settlement we can find out the maximum total settlement by using the previous curves which I have projected earlier. The figures can be used in the following manner. From the nature of the structure, a permissible delta by L is selected. The plots are used to find first the corresponding maximum differential settlement and then the maximum permissible total settlement. Actual estimated settlement should be less than this permissible settlement. Then allowable limits of settlement. Different building codes have specified permissible limits of settlement and angular distortions. These are mainly related to the type of structure and intended use, the type and size of foundation, and the nature of soil. IS 1904 gives limits of the total settlement, differential settlement, and angular distortion for certain typical structures resting either on sand or hard clay or plastic clay. These are presented in the following tables. Like isolated foundations on sand and hard clay. So, depending upon the type of structure, this is the permissible maximum settlement, this is the maximum permissible differential settlement, and this is the permissible angular distortion. For example, if we have steel structures, so for steel structures having isolated foundations either on sand, on hard clay, maximum permissible settlement is 50 millimeter, whereas differential settlement is 0.0033 L, where L is the distance between the columns or it is the distance between the foundations, and this is the shorter dimension. This is the angular distortion 1 upon 300. For reinforced concrete structures it is 50 millimeter, differential settlement 0.0015 L, angular distortion 1 upon 666. Similarly, for plain brick walls in multi-storied buildings, if L upon H is less than 3, 60 millimeter, where H is the height of the wall, this is 0.0025 L, and angular distortion permissible is 1 upon 4000. Similarly, for the case L by H greater than 3, maximum settlement 60 millimeter, differential settlement 0.00033, and angular distortion is 1 upon 3000. For water towers and silos, maximum settlement is 50 millimeter and differential settlement is 0.0015, and the angular distortion is 1 upon 666. Now, similar to this, we have tables for isolated foundations on plastic clay. You will find that these two values for all these structures are similar, only difference is in the maximum settlement, and that is for steel structures 50 millimeter, for reinforced concrete structures it is 75 millimeter, and for plain brick walls having L upon H less than or equal to 3 it is 80 millimeter, greater than 3 it is 80 millimeter, and water tower and silos 75 millimeter. You can see from these two tables that for plastic clay maximum settlement permissible is more than that on sand. Similarly, for the case of raft foundations, the maximum settlement values are given here and differential settlement values are given here, angular distortion when the raft foundations on sand and hard clay. Similar guidelines are available for the raft foundations on plastic clay, like this is for the this is the maximum settlement, this is the differential settlement, this is the angular distortion for various structures. For example, in the case of plastic clay, this for the reinforced concrete structure maximum permissible settlement is 100 millimeter, whereas for the isolated foundation it is only 75 millimeter. If the isolated foundations are on sand it is only 50 millimeter. So, for the raft foundations on plastic clay this value is higher, and also different values of the differential settlement. It can be seen from the tables that a higher total settlement is permissible in clays than in sands. This is explained in terms of the difference in the rate of settlement in sands and clays. The settlement in sand occurs almost immediately on placement of the load, while in clays consolidation settlement occurs over a long period of time. Thus, there is time for structures resting on clays to adjust to differential settlements. In sands, the differential settlement can occur as soon as the total settlement itself occurred, thus leaving the structure no time for gradual adjustment. Then, to determine allowable bearing pressure. So far we have discussed how to determine the safe bearing capacity and how to determine the bearing pressure based on permissible settlement. Then how to find out the allowable bearing pressure, which is the minimum of these two. The allowable bearing pressure is the maximum bearing pressure that can be applied on the soil such that the two fundamental requirements, first is adequate factor of safety against shear failure by which we determine the safe bearing capacity, and settlement within permissible limits are satisfied. It is therefore simple to arrive at the allowable bearing pressure of the foundation as the smaller of the net safe bearing capacity and net safe bearing pressure. Allowable bearing pressure for granular soils. The allowable bearing pressure of a foundation on granular soil is usually governed by the settlement criterion. Unless the foundation is narrow and the soil is loose as for footings on of usual sizes, net safe bearing capacity is quite high. The footings on granular soils are proportioned commonly by the use of N values, the SPT test value. Most of the methods propose empirical equations or charts to determine allowable bearing pressure for a specified maximum total settlement in terms of N values. One such method which is very popularly used is the Peck-Hansen and Thornburn procedure. Peck-Hansen and Thornburn in 1974 have modified the original Tarjagi and Peck 1948 recommendations and presented charts to obtain allowable wearing pressure for a footing of known width B with its base at a depth df resting on the granular deposit, in which n values are measured. The charts take into account both the bearing capacity and settlement considerations. Now, these are the charts proposed by Peck-Hansen and Thornburn. Now, you can see these are the charts for different values of df by b ratio, like this is for df by b 0.25, df by b 0.5 and df by b equal to 1, and this is allowable wearing pressure in kilonewton per meter square versus the width of the footing for different values of n. Now, from this, for different permissible settlement, these are for the permissible settlement of 25 millimeter. So, these charts can be used to obtain allowable wearing pressure for different foundations having different df by b ratio and for the soil strata having different values of n. The initial straight line portion radiating from the origin gives the safe bearing capacity with a factor of safety 2, while the later horizontal portion gives the safe bearing pressure for a permissible settlement of 25 millimeter. Thus, for a given width of footing and n value, the charts makes it possible to determine the criterion governing the design before reading of the allowable wearing pressure. The allowable soil pressure for a footing on sand from settlement consideration is given by qa net equal to 0.44 n allowable settlement SA into Cw, which is the water table correction factor. So, here n is the average corrected n value, SA is the permissible settlement in millimeter, Cw is the water table correction factor that can be determined if we know the depth of the water table below the foundation level. So, this is 0.5 plus 0.5 dw upon df plus bf, it should be less than 1, where dw is the depth of water table below ground level, df is the depth of foundation and bf is the width of foundation. Another correlation is given by Tang. So, Tang's equation is based on Tarjagi and Peck 1948 charts with an additional factor introduced to account for the influence of depth of foundation. The safe bearing pressure Q n rho is given by this particular equation, which reads Q n rho equal to 1.4 n minus 3 in bracket b plus 0.3 divided by 2 b square R w dash C d S a in kilonewton per meter square, where b is the width of the foundation in meters, R w dash is the water table correction factor given by this particular equation. Here d w dash is the depth below the foundation level, n is the corrected n value, that is the n corrected which we determine for a depth of 1.5 to 2 b below the foundation level. S a is the permissible settlement in millimeter. So, for different structures for different type of soils, we know what can be the maximum permissible value that we can use here. C d is the depth correction factor, that is equal to 1 plus d upon b, where d is the depth of the foundation and b is the width of the foundation. d w dash is the depth of water below the base of the footing and d is the depth of foundation. This n corrected is corrected for the by this particular expression, that is n corrected equal to C n into n field, and C n is given by 1.75 by sigma 0 dash plus 0.7 square for sigma 0 dash less than 0 to 1.05. C n is equal to 3.5 upon sigma 0 dash plus 0.7 whole square for sigma 0 dash between 1.05 to 2.8, where the sigma 0 dash is given in kg per centimeter square. Similar correlation are given by Meyerhoff, and Meyerhoff in 1974 proposed the following relationship: Q n rho equal to 0.49 n RD1 SA in kilonewton per meter square if the width is less than 1.2 meter, and if width is more than 1.2 meter, then this Q n rho equal to 0.32 n RD2 B plus 0.3 upon B whole square into SA, where RD1 is the depth correction factor, which can be determined like this: 1 plus 0.2 d upon B, it should be less than 1.2, and RD2 is depth correction factor 1 plus 0.33 d upon B, it should be less than or equal to 1.33. Meyerhoff did not include the water table correction factor for the reason that the values of n corrected below the water table already reflect the effect of water table. Some correlation given by Bowles are shown below. He recommends an increase in 50% in the value obtained by Meyerhoff and proposed the following equation. So, this is nothing but Meyerhoff equation, only thing is it is an increase, there is an increase of 50%. So, this Q n rho is given by this expression for B less than 1.2 meter, and Q n rho is given by this expression for B greater than 1.2 meter. Bowles recommends that the field n value must be corrected for overburden, but not for must not exceed the twice the field value. In any case, this should not be more than 2 times the field value. Now, different terms used in the Bowles equation are: B is the width of the foundation, RW dash is the water table correction factor given by this expression, n is the corrected n value, SA is the permissible settlement, CD is the depth correction factor which is given by this expression, dW dash is depth of the water table below the footing, and D is the depth of foundation. N corrected can be determined from the n field using these relationships. When sigma 0 dash is between 0 to 1.05 kg per centimeter square, we can use this expression, and for values between 1.05 to 2.8 we can use this particular expression to find out the value of a correction factor. Then correlation for the raft foundation. A raft or a mat foundation covers the entire plan area of the building. It is used when individual spat footings cannot be used either because of heavy loads or poor soil conditions, or both. Because of its rigidity, a raft tends to bridge over local soft pockets or any other heterogeneity of the strata, and the irregularities tend to get evenly distributed below the raft. Owing to these reasons, a raft foundation suffers much less differential settlement than when isolated foundations are provided. It is therefore natural that the safe bearing pressure for a raft foundation should be much higher than for an isolated foundation for the same limit of differential settlement. Putting it in another way, it is possible to have a permissible total settlement for a raft almost twice that for an isolated foundation, but still have the same differential settlement resulting in both the cases. A foundation with its width 6 meter or more can be classified as a raft foundation. The allowable bearing pressure of a raft on a granular soil is always governed by the settlement considerations. Tanks gives the following equation for allowable bearing pressure on the raft foundation: Q n rho equal to 0.7 n minus 3 RW dash CD into SA in kilonewton per meter square, whereas Peck-Hansen and third one equation is Q n at equal to 0.88 n SA into CW kilonewton per meter square. Above equation underestimates the allowable bearing pressure for n greater than 50. For n less than 5, that is, for a very loose deposit, the soil requires densifying before a raft can be used, or the raft may be supported on the piles. Allowable bearing pressure for cohesive soil in the case of raft foundation. Field tests have limited relevance to the cohesive soils for the reason that these tests, being essentially short duration tests, cannot reflect in a realistic manner the consolidation settlement characteristics of a clay soil. Both the safe bearing capacity as well as settlement are determined by using appropriate shear strength and consolidation parameters obtained from laboratory tests on undisturbed representative samples of clay. It is not easy to say whether the allowable bearing pressure will be governed by the net safe bearing capacity or the net safe bearing pressure in a cohesive soil. The usual procedure in proportioning a foundation on a clay soil is to select tentatively the dimensions of a foundation by using the net safe bearing capacity. It may be noted that unlike in granular soils, the bearing capacity is not affected by the size of foundations in clay soils. The net safe bearing capacity is determined for phi equal to 0 condition, which represent the most critical situation. The undrained shear strength Cu is determined either from in situ vein shear test or the unconsolidated undrained test or the unconfined compression test. The net safe bearing capacity is then assumed to be the load intensity acting on the soil at the base of the foundation, and the magnitude of settlement is estimated using the compressibility parameters of the soil. If the estimated settlement is within the permissible total settlement for the structure, the dimensions of the foundation assumed for the analysis are adequate. The dimensions of the foundation may be increased if the settlement criterion is not satisfied. Raft foundations used below one or more basement floors offers a very practical foundation choice when the loads are heavy and the clay soil is soft. When basement floors are constructed, the excavated soil is not backfilled. The net loading intensity transferred to the soil can be equated to the net allowable bearing pressure. We call it as the floating foundations. Then this Q upon A minus gamma dF will be equal to QA net, where Q is the total superimposed load, A is the area of the raft, gamma is the unit weight of soil, and dF is the depth of the base of the raft. The base of raft can be located at such a depth dF that the allowable bearing pressure of the raft is sufficient to take care of the net load intensity at that particular depth. Such a foundation is known as a partially compensated or partially floating raft. The net load intensity would reduce to 0 if Q upon A is equal to gamma dF. In such a situation, the soil is not called upon to resist any load. The superimposed load due to construction is fully compensated by the weight of the soil itself, which is excavated but not backfilled. Such a raft is called a fully compensated or floating raft. Theoretically, such a raft should not settle at all. However, in practice, after the soil is excavated, there is some heaving of the soil because of the load release, and this shall manifest itself as settlement after the structure is raised. The principle of load compensation can be used with advantage even in the case of loose granular soil deposits. The net safe bearing capacity of a raft foundation on a cohesive soil is usually determined by the Skempton's equation. Settlement of a raft on a normally consolidated clay can be very high even for a low load intensity. Now, there are some guidelines given in the IAS code for the location and the depth of the foundation, which have to be observed when we select the depth of the foundation and also the distance between two footings. Foundations must be properly located and placed at such a depth that its performance is not adversely affected by the factors such as lateral expulsion of soil from beneath the foundation, seasonal volume changes caused by freezing and thawing, and presence of adjoining structures. As a general rule, any foundation must be placed at a depth where the soil stratum is adequate from point of view of bearing capacity and settlement criteria. Further, foundation must be placed below the zone of swelling and shrinkage, which is crucial in the case of black cotton soils, and below the zone of frost heave in case of sands and silts in the areas where extremely low temperatures are likely to materialize. IS 1904-1978 have given recommendations for the location and depth of the foundations. As per the recommendations, the minimum depth of the foundation should be 50 centimeter. When the ground surface slopes downwards adjacent to a footing, the sloping surface should not encroach upon a frustum of bearing material under the footing having sides which make an angle of 60 degree with the horizontal for rock and 30 degree with the horizontal for soil. The horizontal distance, that is the edge distance from the lower edge of the footing to the sloping surface, must be at least 60 centimeter for the case of rock and 90 centimeter for the case of soil. Now, if the footings are at different levels, then we will have to observe these recommendations. Let us say you have got a sloping surface and there are two footings, this is the upper footing and this is the lower footing. Then the slope of the line joining the bottommost edge or bottommost corner of the upper footing and the bottommost corner or the edge of the lower footing, it should not be steeper than 2 horizontal to 1 vertical. Now, if the footings are at different levels in the clayey soil, it is recommended that for this bottommost edge of the upper footing and the line joining the bottommost uppermost edge of the lower footing, the slope should not be steeper than 2:1, 2 horizontal to 1 vertical. Now, suppose it is proposed to place a foundation adjacent to a old structure, like we have an old footing which is here and now we want to place another new footing, then we will have to observe these two criteria. Number 1, this is the spacing or the distance of the footing from the center line. So, S should be larger of B1 or B2, where B1 is the width of the old footing and B2 is the width of the new footing on the average soil. And when we join the bottommost edges of the old structure or old footing and the new footing, this slope with the horizontal should be 35 degrees when the new footing is on the average soil, and this should be equal to 45 degrees when the new footing is on the poor soil. The steps involved in the proportioning of the footing can be summarized now as below. It is essential to estimate the dead load, live load and other loads such as wind load or seismic load that act on the foundation. It is a common practice to assume that the wind load and the seismic load do not act simultaneously. Moreover, since some live loads are temporary and transient, it is necessary to include only that part of the live load that may actually induce settlement in the foundation soil. For this reason, in the case of clay soils where the settlement is time dependent, it is enough if the design is carried out for a reduced value of live load, this being defined as the live load acting for the major part of the life of the structure. Generally, 1/2 of the design load is taken as permanent. However, for foundations resting on coarse grained soils, the maximum live load that can ever occur is considered, irrespective of the duration of such a load, since settlement can occur in a very short period in such soils. The bending moment at the base of the column or wall, if any, should also be determined. A square footing is preferred where only axial loads act. If the footing is to be designed for bending moment also, in addition to the axial load, a rectangular footing is more suitable. The depth of foundation is fixed suitably by considering the nature of the structure and the subsoil conditions as revealed by the borehole log data. The proportioning of a foundation is a problem which is interactive in nature. The typical structural engineer's approach of obtaining the plan dimensions by dividing the column load or wall load by the so called bearing capacity cannot be used here. Suitable plan dimensions, namely the width of a square or a strip footing and the width and length if the choice is rectangular footing, have to be assumed to begin with. For this assumed plan area, the net loading intensity Qn is equal to the design load divided by the plan area. Qn should not be allowed to exceed the net allowable bearing pressure Qa net, that is, Qn should always be less than Qa net. If it does, the design is unsafe. On the other hand, if it is very much less, that is Qn is far less than Qa net, the design is oversafe and hence uneconomical. The proportioning of a footing is thus a process of optimization, ensuring both safety and economy. Since Qa net is the smaller of the net safe bearing capacity from shear consideration and the safe bearing pressure from settlement consideration, both the considerations will have to be factored in the design. For the assumed dimensions and depth of footing, the net safe bearing capacity Qns can be calculated on the basis of soil data obtained from the test and using the methods discussed all through the lectures on shallow foundations. In granular soils, the standard penetration test or plate load test gives the data required for this purpose. The n value to be used is the average of the corrected n values from the base of the footing up to a depth equal to the assumed width of the footing. For clay soils, the average undrained shear strength Cu required as input in the bearing capacity equation is obtained from laboratory shear test on undisturbed samples. Check if Qn is less than Qns. If not, the dimensions of the footing need to be revised and step is repeated till the check is OK. The total or maximum settlement of footing in a granular soil is determined using the methods with n value or the plate load test data as basis. The safe bearing capacity is used as the pressure inducing settlement in the settlement computations. The settlement in a clay soil is determined with the safe bearing capacity assumed to act at the base of the footing using consolidation test data. An estimate is also made where required of the differential settlement between various footings and the angular distortion between various parts of the structure. The maximum settlement, the differential settlement and the angular distortion obtained are compared with the permissible values or any accepted code of practice. If they are not within the permissible limits, the safe bearing capacity is revised and the settlement computation is repeated to ensure that all requirements are met. The stability of footing is checked to ensure safety against sliding and overturning. The factor of safety should not be less than 1.75 against sliding and not less than 2 against overturning. When only dead load, live load and earth pressures are considered, it must now be clear why it was said earlier that the proportioning of footing is an interactive procedure. Unless the depth of footing and tentative dimensions of the footing are assumed, the average and corrected n value cannot be worked out. Also, the soil strata forming the seat of settlement and their thickness are also dependent on the assumed values of depth of footing and the width of the footing. Some investigators believe that while the bearing capacity can be calculated by considering the soil stratum or strata included within a depth b below the base of the footing, the settlement computation should be done by considering the seat of settlement to be at least 1.5 to 2b below the footing base. So, following the steps discussed earlier, we arrive at the dimensions of the foundation. Now, I am going to discuss few solved examples. by which it will become more clear how to obtain the allowable bearing pressure of foundations. Now, this is the solved example on secondary consolidation first. The void ratio at different elapsed time from a consolidation test data for a stress range of 25 to 50 kilonewton per meter square is given below. Now, here these are the void ratio versus elapsed time. Actually, in the consolidation test we get readings corresponding to different time interval. Now, by using either height of solids method or change in void ratio method, we can determine the void ratio corresponding to that reading. So, these are the direct void ratio obtained from those readings. So, for example, here at the start the void ratio is 1.732, after 0.25 minutes it is 1.710, after 1 minute it is 1.692, similarly after 8 minutes it is 1.625, after 60 minutes it is 1.52, and after 500 minutes it is 1.470. So, we will be using this data to determine secondary consolidation settlement. The load increment in the test represents the anticipated stress range in the field. The primary consolidation may be assumed to be completed after 25 years, as we know that the secondary consolidation settlement is dependent on the time, not on the stress range, but it occurs at the constant effective stress. The thickness of compressible layer at the site is 8 meters. Compute the amount of secondary consolidation settlement for a period from 25 to 100 years after the construction. So, first of all what we do, we plot this data on E versus log of time curve, and then by these two portions we draw a tangent here and then the tangent here, we get the point corresponding to 100% degree of consolidation. Now, this particular portion from here to here, it represents the primary consolidation, whereas this represents the secondary consolidation. Now, in order to find out C alpha, we find out the slope of this line corresponding to 1 log cycle, and corresponding to 1 log cycle whatever is the delta E, which we can read from here, that is the C alpha coefficient of secondary consolidation. So, this figure shows the void ratio plotted against log of time t. C alpha is equal to delta E when delta log t corresponds to 1 full log cycle. From figure, the C alpha has been found to be 0.033. The void ratio EF is the final void ratio after the consolidation process is over. At the end of primary consolidation, we can read it from that figure, it comes out to be 1.495. Then secondary consolidation settlement is obtained by this equation C alpha delta log of t upon 1 plus EF into H0. When we substitute all these values, we will get this as the secondary consolidation comes out to be 0.064 meters. This is a solved example on the Peck, Hansen and Thornton procedure. A 3 meter wide footing is resting at a depth of 1.5 meter below ground level on coarse sand stratum having unit weight as 1.8 ton per meter cube. The groundwater table is encountered at a depth of 3 meter. The submerged unit weight gamma dash of the coarse sand below water table is 1.8 ton per meter cube. A layer of fine sand gamma dash equal to 0.8 ton meter cube lies beyond 4.5 meter depth. The observed n values are given as below. This is the depth below ground level and these are the observed n values. 0.75 meter it is 8, 1.5 meter it is 10, 2.25 meter it is 15, likewise 5.25 meter it is 16 and 6 meter it is 25. The allowable settlement for this foundation is 40 millimeter. The average n value of n corrected between elevation 1.5 meter and 6 meter below the ground surface will be considered for the calculations. This would mean a depth equal to 1.5 b or 4.5 meter below the base. The field value of n are corrected first for overburden pressure and then for dilatancy using the Peck, Hansen and Thornton procedure. It may be noted that the dilatancy correction is not required in the case of coarse sand layers. So, these calculations are done in the tabular form as shown here. First of all, in order to find out the overburden correction, we will have to find out overburden correction at that particular level. So, knowing the submerged unit weight of the soil or the effective unit weight of all the soils above the point under consideration, we can find out this overburden pressure as gamma into D. So, from that we can find out the Cn as per the Peck-Hansen-Thorndman procedure. So, corrected the n values in the field are given here, and n corrected for overburden will be equal to Cn into n. So, we apply this correction factor. Then after getting this, we apply the correction for dilatancy. Now, when we apply correction for dilatancy, we know that the dilatancy correction in which the rate of dissipation of pore water pressure is very high in the case of coarse sand. So, we do not apply dilatancy correction for coarse sand. After getting this, we get the average n value of the n corrected, and that is equal to n double dash we use for the. So, this will be equal to summation of all these values divided by number of values. So, it comes out to be equal to 18. So, this n corrected value is used for the calculation of allowable bearing pressure. Now, for dF by B equal to 0.5 and B equal to 3 meter, the allowable bearing pressure corresponds to the horizontal portion of the plot of Peck-Hansen-Thorndman. Hence, settlement criterion governs the design. In order to determine Q and at, we use this particular relationship 0.044 Cw n into SA ton per meter square. Now, here n corrected we have found it comes out to be 18, and permissible settlement given is 40 millimeter. This water table correction factor can be determined by this equation, and it comes out to be 0.83. When we substitute all these values, we get the QA net as 26 ton per meter square. It means that foundation can be designed for an allowable bearing pressure of 26 ton per meter square. It should be remembered that Peck-Hansen and Thorndman use a factor of safety of 2 on ultimate bearing capacity. If the factor desired is the usual value of 3, Q ultimate can be computed by obtaining the bearing capacity factors NQ and N gamma from N and use in the bearing capacity equation to obtain the ultimate bearing capacity and then obtain the safe bearing capacity. This is another solved example that uses the IS recommendations. Now, in order to determine net allowable bearing pressure of the footing, in the previous example using the IS code recommendation, we use this N corrected as 18. So, after Peck-Hansen and Thorndman 1974, for n equal to 18, phi is 33 degrees. Now, for phi equal to 33 degrees, we can obtain parameters NQ and N gamma using this particular chart. So, here this is the N value, and from this N value we can find out angle of shearing resistance, and from angle of shearing resistance we can find out values of NQ and N gamma. Then we also apply the water table correction when the water table is below the base level of the foundation using this particular plot. So, we find out this RW2, this we have already discussed. So, here in this case this is the depth of the footing, this is the depth of the water table below the ground level, and we consider this width equal, this depth equal to equivalent to the width of the footing, and depending upon dW2 by B we can find out RW2. So, for cohesionless soil C dash equal to 0, Q net ultimate is given by Q NQ minus 1 SQ dQ plus 0.5 gamma B N gamma S gamma D gamma into RW2, where Q is the overburden pressure at the foundation level, that comes out to 1.8 into 1.5 2.7 ton per meter square. RW2 from the previous figure it is 0.75, and safe factors are determined by using the procedure given in IS code, and the expressions are like this: SQ equal to 1 plus 0.2 B upon L, S gamma equal to 1 minus 0.4 B upon L. When we substitute different dimensions, we will get this as 1.12 and S gamma as 0.76. dq equal to d gamma is given as 1 plus 0.1 df upon b 10 of 45 plus 5 by 2, and we can obtain it as 1.09. When we substitute these values and using the method suggested by IS code to determine the allowable bearing pressure from the settlement criteria, we use this particular chart for the given width and the value of n, we can find out what is the settlement in meter per unit pressure kg per centimeter square. So, first of all we find out Q nu, that comes out to be 116 ton per meter square. Q net safe is Q nu divided by factor of safety, that is equal to 38.7 ton per meter square. So, for n equal to 18 and b equal to 3, using the previous plot we can find out the settlement for a pressure of 1 kg per centimeter square or 10 ton per meter square, that comes out to be 15 millimeter. Taking into account the position of water table, actual settlement will be equal to 15 millimeter divided by correction factor, that is equal to 20 millimeter. For SA equal to 40 millimeter, Q n rho will be equal to 10 upon 20 into 40, that is 20 ton per meter square. Hence, Q A net using IS recommendation will be equal to 20 ton per meter square. In this manner we can determine the allowable bearing pressure of the foundations. So, in the last few lectures we have discussed about the theories related to the shallow foundations, and especially the Terzaghi bearing capacity equation and the modifications suggested by Meyerhoff, Hansen, Brinch-Hansen, Thornburn, the IS code procedure to determine the bearing capacity of foundations. Then we have also discussed how to determine the settlement of the foundations and what should be the permissible settlement, and then we have also discussed the procedure or step by step procedure to find out the dimensions of the foundation. So, it covers the entire component of the syllabus of the shallow foundation, which is taught in the undergraduate course. Thank you very much.
Thank you.